Hi everybody, and welcome to exercise 4 on the list of final exam review problems. This is an exercise that goes way back to the very first couple of weeks of the course where we're trying to decide whether subsets are subspaces of a vector space. Okay, remember that a subspace is like a subset of a vector space that is itself a vector space. It has the properties of that. Okay, and we had kind of a standard tool for deciding when a subset is a subspace. It was called Theorem 1.3. You'll discover with some of these problems we're going to use that approach, and then for some of them it might be convenient to come up with a different strategy for doing it. And in this video we're going to focus just on parts A and B of this problem. Okay, so let's start with part A. So they're giving us a vector space R3, and they'd like us to decide whether this set W is a subspace of R3 or not. Does it have the right properties? Okay, so we could use Theorem 1.3 on this. That was the one that said we need to kind of verify three things to show that this is a subspace, that it contains the zero vector and that it's closed under addition and scalar multiplication. It's actually easier, though, in this problem to use a different technique. Okay, there was a theorem that we had that said that the span of a set of vectors is always a subspace. And so that's the strategy that I'm going to use here. I'm going to try to demonstrate that W can be expressed as the span of a set of vectors. Okay, and to get started down that road, we might notice that 3a plus b plus 4c equals 0. We can rewrite that equation, okay, most conveniently by taking the variable b and just solving for it. So b would be equal to negative 3a minus 4c. And what that gives us, let's first start with our claim. So I'm claiming that this is a subspace. Okay, and to do that, notice that we can rewrite W using that observation that we just made as the set of ordered triples that looks like A, and then since B is equal to negative 3A minus 4C, okay, we can just substitute that in for B. So essentially what we've done is to reduce this down to just a set of ordered triples that depends on two variables, A and C. Okay, but we can rewrite that. We can kind of pull that apart and rewrite that as A times 1, negative 3, 0, plus C times 0, negative 4, 1. And notice that by doing that, we have demonstrated that W is a span. This is, by the very definition, the span of the two vectors, 1, negative 3, 0, and 0, negative 4, 1. Okay, and so now we just need to find the theorem that says that if you can express a subset as the span of a set of vectors, it's automatically a subspace. We don't even need to check the properties. Okay, and if you look back on your theorem list, you'll discover that that's what Theorem 1.5 says. Okay, so we conclude that W is a subspace of V by Theorem 1.5. Okay, and that's part A. So let's move on then to part B here. Okay, this is a very different vector space. So now V is the set of all 2 by 2 matrices with entries in the real numbers, and we'd like to check to see if the set of all matrices, A, that satisfy this relation, the transpose of A times A is equal to the identity, is that a subspace? Okay, well, take a minute and think about that maybe. Okay, if you think about the very first property that's required in order for a set to be a subspace, we need the zero vector to be in that subset. Is the zero vector in W in this case? Okay, well, I guess to answer that question, we have to first ask ourselves, what is the zero vector in V? You can look back or convince yourself that the zero vector is just the zero matrix, and ask yourself, if you took the zero matrix and kind of substituted it into this formula, took its transpose and multiplied it by itself, would you get the identity matrix? I think you'll agree that the answer to that is no. Okay, so we claim that W is not a subspace in this case. Okay, and so to do that, we're going to give a counterexample. It's going to be the counterexample that I described in words. Okay, so to see this, let's let A be the zero matrix. I'm going to write that as just 0M. Okay, the zero matrix. Okay, and if we just take that with that choice of A and take A transpose times A, that's going to be taking the zero matrix transpose times itself. That's just going to give you the zero matrix again. You take two matrices that have a bunch of zeros in them and multiply them by itself, you're just going to get a bunch of zeros again. Okay, and that's clearly not equal to the identity matrix. Okay, so we've just demonstrated then that this choice of A, the zero matrix, is not in that set. Okay, it's not in W, and therefore this can't be a subspace. Okay, and I think we're done with part B.